Everything we've done up until now is being done with the intent to make good decisions. All of the statistics we've covered so far are centered around figuring out how to decide on something. So the approach to making data-driven decisions is called hypothesis testing. And what I need to do is I need to say, hey, I have an idea about my population. I want to test that idea. And then I check the data to see if the data agrees with my idea or disagrees with my idea. Now, really, if it agrees, I'm happy. Maybe it doesn't agree perfectly, so I have to play with the hypothesis a little. And sometimes that's the big cycle. Page 318, we have this picture. I have an idea, create a hypothesis, I get my data. Oh, hey, wait a minute, what's this piece down here? I test something. I calculate a statistic from my data, like we've been doing, means, medians, proportions, standard, whatever it is I'm looking at. I then make my decision and then move on from there. Ideally, this repeats several times as we refine our ideas. So there are a couple of places in here where we need to know what our hypothesis is, what test we're making, how do we make our decision? We have to decide all of these pieces in order to make a worthwhile decision. My hypothesis the thing I think is going on. It's called the null hypothesis. H0. Now, I could be right, could be wrong. So if this is what I think is happening, its opposite is the alternate. Our book calls that H1, but I've also seen it called HA. I need to decide what level of consistency or alignment with my assumption I need. And I will decide what level of inconsistency requires me to choose the alternate one. So I have a decision level. My decision level is how consistent with my idea. How close do I have to be to say, all right, I'm going to go with my idea was right? How far off do I need to be to say, nope, my idea is wrong, it's inconsistent, reject my assumption and pick the other one? That decision rule comes from our desired confidence level. Now, I need to know some things about my hypothesis. I need you to go back and remember some terms from our data and our measurement levels. Okay. I need these two assumptions, H0 and H1, must be mutually exclusive and completely exhaustive. What does that mean again?
They can't happen at the same time, and then like they both happen in the morning.
If I was strictly thinking about probabilities, right? Yeah. So I would say we have only these two choices. Nothing else could happen. And they can't both happen together. Like guilty, not guilty. That's the only decision the court can come back with. You go to the NCAA, you take a drug test. Did it come back positive or negative? The security alarm, did the alarm go off or not? But now I have the thing I think is true, it's alternate, and I'm going to pick one over the other based on my decision rule. What do I do with my decision rule? Well, let me go back to those three examples. In a jury trial, when is a jury going to find something guilty? What's the standard for a jury trial? Depending on what kind of trial. Criminal cases are beyond a reasonable doubt. Civil cases are preponderance of the evidence. The drug sample for the NCAA. My sample contained more than the maximum level of the drug. I detected it. That's a positive test. Security system. A fingerprint, biometrics like your MacBook or your phone, if you still use a fingerprint unlock, your print has to have, I think the Apple one had 20 points. If you differ or if you don't match the 20 points, doesn't let you in. Face ID actually measures over 120 points. So my decision rule is going to be based on the type of decision I'm making and what my hypothesis and alternate are. Uh-oh. I don't know what that is. Something crashed. It looked like a Google Drive crash report, so it doesn't seem to have affected this. My recording is still in progress. I'm going to keep my fingers crossed that everything works. So we're going to have to decide what our decision rule is each and every problem we look at. Once we have that decision rule, we then gather our data, decide, and take action based on that decision. Now, in that data gathering, I also do a computation. What is my average? What is my proportion? What is my standard deviation? It depends on the situation. What's my variance? Maybe I calculate a number of different things. Maybe I'm just doing a survey and I'll look at which category is the highest and move on from that action. But I calculate something and then I decide. Now, here's an interesting statement. I don't ever prove anything here. I just gather evidence in favor or against my assumption. Statistics don't prove jack. They suggest. They confer. Most of the time, I can repeatedly test my hypothesis. The exception is a criminal trial. You only get one shot at that. It's a rule called double jeopardy in the American judicial system. So I can continue to demonstrate support of my idea, but I can't really prove it. So let's consider what could happen. There are really two options. My assumption is true, or my assumption is false. Let's say I gather all my data, I gather my information, I compute some stuff, and I decide to reject my hypothesis. Or I decide, no, there isn't enough evidence against it, I'm going to keep it. So those are two other options. I could reject my null hypothesis, or I could accept it, which is really fail to reject. So those are also separate options, which really, that looks like a familiar layout. Okay. Right here in this box, my null hypothesis was true and I didn't reject it. That's a good choice. There's another good choice up here. Where's my other good choice? Max?
H0 is false.
Ah. So now let's think of what the other two boxes are. My assumption is true, but I rejected it. This is a problem. We're going to call this a type 1 error, or a false positive. Oh, my assumption is that you are clean. When I go to do your drug test, you are clean, but I reject that assumption. Your test showed something unusual. I reject that assumption. That's a false positive on your drug test. That makes sense why I would call it a false positive. I had something true and I said no anyway. I rejected something true. What's my last box? I accepted something false. Oh, okay. It shouldn't have been accepted. This is a type 2 error. Now, let's think about the consequences here. I have a trial. The assumption in a trial is that you are innocent. What's a false positive there? The assumption, my null hypothesis, you are innocent. What's this error?
Someone hasn't done anything.
I put an innocent person in jail. You are innocent, but I rejected that, put you in jail. What's this error? Which is, who did it, right? Somebody guilty goes free. The American judicial system says that it is much better to make this error than this error. The principle of a jury trial says it is better to let 10 guilty persons go free than to put one innocent in jail. That's what law school tells you. Drug testing. What's this error? A false positive, and so you can't play. Maybe you get fined. Maybe your team gets fined. Some disqualification occurs, right? What's this one? They don't catch you at it, right? So somebody dirty gets to play, Lance Armstrong, right? Somebody, until they get caught, they got through it. Our security system. I put my fingerprint on. What's this error? They don't recognize me. I don't know if you've had this option on your MacBook where you open it up, you put your finger down, it goes try again. It means your finger's not in the right place. It doesn't know you from that print. What's this error? Not your finger, but they still let you in. This looks like the table from that question on the exam. And we calculated probabilities based on that stuff, right? So I want to think about two different probabilities that are up here. Probability that we reject the null hypothesis and we given that it is true. Now, I don't actually have a spot on this chart that totals everything up. But let me think about where the pieces that would go into this probability would live. What parts of the table would I use to calculate that number?
Like the type one error over whatever the total of like the each column would be.
I would just look at this column and take this over whatever this total was. So what this is the chance of making that error. We'll call it alpha. And that's our chance of making a type 1 error. This is called significance. Hey, wait a minute. Heard that phrase before. Level of significance. That went with my confidence interval idea. I have another probability, the probability that I accept or fail to reject my null hypothesis when it's true, when it's false. We'll call this beta. What's this? Because that would be this in this column. Normally, we call 1 minus beta the level of sensitivity. Or power. So if beta is the chance of making a type 2 error, 1 minus beta is the chance we got it right. That would be this part. The good choice. Problem. A test that is more powerful. More power means this gets smaller, right? Fewer false negatives. Fewer false negatives usually mean more false positives. You don't let people slip through. You set up the thresholds to be tighter. You get more false positives that way. So there's a trade-off between alpha and beta. If I make the test harder to pass, then it's more sensitive. What happens? Hey, wait, COVID wasn't all that long ago. If you stick the swab up your nose and take the test, and the test is very sensitive, very powerful, what's more likely to happen is that that test is going to come back positive. You could be clean or have very low levels. You were exposed 7 or 8 months ago and you've been healthy ever since, but you still have a little bit in there. The more powerful the test is, stronger the chance of a type 1 error. Smoke detectors. What happens if you crank up the sensitivity on a smoke detector? It goes off. What about carbon monoxide detector, right? Beeps all the time. So there's a trade-off here. The more sensitive the item is, the more chance there is to a false alarm. So a smaller beta means a larger alpha, and vice versa. A smaller alpha means a larger beta. More often than not, we're concerned more with type 1 errors than type 2 errors. So we make the trade-off to have fewer false positives. And then to make our beta smaller, we gather more evidence. We do more tests. And that's why when you were doing COVID tests, you were asked to do them twice. You didn't just do one test. You took 2 of them. What are the consequences? Question 5. What are the consequences of a false negative if we inspect your car's brakes? Now, if we didn't know what the consequences of an error are, I have to know the null hypothesis. The null hypothesis for this question is, we look at your brakes are fine. What's a false negative mean in this situation? So your brakes are bad. Aha, wait a minute. My assumption for a type, say again, which one error? A type 2.
Yes.
So say it again.
Oh, your brakes are.
My assumption H0 is your brakes are fine. So what's it mean to be here?
Like your brakes are bad, even though they're good. No,
Your brakes are bad, but they say they're good. What happens? You go for a drive and have an accident. Right? That's a big cost. So if you're a mechanic, this is a bad error. somebody's going to say, hey, you told me my brakes were good. I was out there that afternoon and I couldn't stop. Now, what's this error? Which means you have to pay for a brake job when you don't need one. That's going to cost people money, right? But that's going to be a lawsuit. Which error do you want to make fewer of? So you look at the situation, look at what your consequences are either way, and then you can decide what's the risk I'm willing to take. Back in the 70s, Ralph Nader made his mark investigating a car, the Ford Pinto. Anybody hear of the Ford Pinto? What'd you hear about it, Austin?
It didn't really work out very well. Exploded, I think.
There was this little problem that they put the gas tank between the bumper and the rail. So if you got rear-ended, the gas tank broke open and the car blew up. Ford decided it was cheaper to deal with the lawsuits than have a recall. So rather than recalling the hundreds of thousands of Pintos that were out there and putting in a reinforcement plate between the bumper and the fuel tank, they just said, oh, screw it, we'll settle the lawsuit. That's a hell of an error, isn't it? But they weighed the decision, which would be more financially responsible as a company. Ralph Nader broke this lawsuit wide open. That's why he ended up being a very popular person and thus became what would eventually be a presidential candidate. Questions? I hope to never be in a position where a decision I have to gather statistical data for is something that is critical enough to decide whether or not somebody lives or dies. And since I teach math, that's really, really, really unlikely. But if I go to work for a company, maybe I work for PNC Bank, maybe I work for an health management company, maybe I work for Blue Cross Blue Shield, maybe I work for the Rand Corporation and I do statistical analysis for them. At some point, I either have to make a decision based on this data or I have to understand the data to justify the decision. And those data, those pieces of information can be life-threatening or life-saving. That's going to be our next question. How do I make this decision? Yes. And yes, the smaller beta is, the larger my sensitivity gets, because sensitivity is 1 minus beta. So small beta, very sensitive. So now the question is, how do I come up with my decision? Where do the numbers show up in this? Right? Because I can't make a decision until I've gathered some data, calculated something, and checked whether or not it matches how close I want it to be. So I need a decision rule based on my hypotheses. Now, we're really talking about statistical hypotheses. Fine. Leave you upside down for a minute. A statistical hypothesis is a statement about a parameter. Some parameter in my population. So I could say, I expect the average on the next exam to be. I want the average weight of a bag of flour coming off my production line to be 1,800 grams. Something like that. A hypothesis test is some decision between our two competing, exhaustive, exclusive hypotheses. So let me pick an idea out of thin air. I claim the average for something is 5. Then I do a sample. And when I take the sample, I then get to do a computation. And the computation I get to do is the average for my sample. And now we ask the question, how close is close enough for me to accept or reject that hypothesis? Ah, there's my null hypothesis. Well, if my assumption is that I have a parameter equal to a particular value, that's my benchmark. This is usually based on prior knowledge. Something about the way the machine is set up, something about the population that we already know. It's some sort of targeted value we created. That's something we establish separate. If I give that null hypothesis, what's the alternate hypothesis?
Something other thought.
Now, there are really 3 different ways to write a null hypothesis for an average. We're going to do averages now. We'll do proportions later. We'll look at other types of statistical calculations even later. Why are you messing? We could use a null that is exactly the one we were just looking at. Our average is some number, which I'm going to call mu0. That's our benchmark. But we could also say, hey, our number is always less than or equal to this. Or our number is always bigger than or equal to this. If these are my null hypotheses, H0, what are the alternate hypotheses in each case? Well, the middle one's the one we just did. It's something else. But if my hypothesis on the left, the mu is less than or equal to this, what's the alternate? And what about here? Those are literally just the opposites of the statements above them, right? But now I think to myself, hey, wait a minute. When I do a sample, samples are normally distributed. So I can think about this using a normal curve. Samples are always normally distributed. If I had something that looked like this middle version, the alternate hypothesis doesn't tell me whether my number is too low or too high, just that it's something different. I said the average was 5, maybe the average turns out to be 4, maybe the average turns out to be 7. But it could go in either direction, right? If it goes in either direction, then we will have to be way out on the edges of my normal distribution. Horrible picture, I know. But what this means is that I say to myself, oh, when we're out here, that's bad. If I'm way out there, away from my average that I thought it was going to be, mu 0, right there in the middle, I thought we were going to be there, but instead we're far away from that, then I should reject, shouldn't I? So this area right here, these are my rejection zones. And I have some number here. Some number on the left and some number on the right. And those are my critical values. Now, those critical values are going to be what kind of numbers? What variable will we use for those critical values? Because they're on my normal curve and they define a spot on the bottom of the x-axis. Those should be z values. Now, how does this picture change if I'm here? Advantage. The only thing that changes here is the zone and the critical value that goes with it. In this normal picture, where's my rejection section? Where's my alternate show up? Which side? So we'll be over here. greater than. So here's our rejection zone, and here's our critical value. Critical value, rejection. There's only one other picture left. This picture over here. Same question. My alternate is mu is less than some number, means I should reject if we're too far off to this side. I hope it is to no one's surprise. This is called a right tail test. This is called a two-tail test. And this is called a left tail test. I freely admit to being a crap artist. Page 325 has a much better picture than I do. Our left tail test, rejection area, critical value. Two-tail test, rejection areas, critical value. Right tail test, rejection area, critical value. Now they did something I didn't do. There are alpha on these pages. The hell was alpha again?
Answer the type 1 error.
Which meant that we rejected it, but it was true. I want that to be small. Yes, I don't want to convict someone who is guilty. So I would like a small chance of rejecting and a large chance of not rejecting. Like this. But if I'm doing a one-tail test, whether it's right or left, then I only look at one side. And so all of that area shows up on one tail. But if I look at a two-tail test, then I have to split it. Hey, look, half of it's in the bottom and half of it's in the top. I seem to remember using Z alpha over 2. Where was I using Z alpha over 2?
Finding the Z-coordinate intervals.
To do our confidence intervals. Exactly. I used Z alpha over 2 when I was looking at both sides, and I said, oh, it should be in here. Hey, wait a minute. That's these numbers, aren't they? How far out to the left or the right should I be able to go and still make it work? Now, the difference between a one-tail and a two-tail. A two-tail creates a confidence interval. It says you should be in here. A one-tail just does 1/2 of the confidence interval, and it moves it further in because this tail is bigger here than it is here. So there's a lower threshold for one tail. There's a higher threshold for two tails. I got to figure out how to find these critical values. I got to figure out how to find these critical values. Questions? A note. Up here, I said our assumption was that the average was 5. That's a two-tail setup. If my null hypothesis is that my average was less than or equal to 4. And then I take my sample. I get something that's very, very, very much larger than 4. Then not only will I reject my null hypothesis, I would reject any null hypothesis that gave me a benchmark smaller than 4. So once you tell me, hey, no, 4.0 is wrong, then anything like 3.5 would also be wrong. 3.9 would also be wrong. Any benchmark less than the benchmark we've just rejected doesn't cut it. In a lot of cases, we don't normally care whether we know it's too big or too small. We just care if it's right or not. More often we do a two-tail instead of a one-tail. Why? I don't care if you drilled the hole too small or too big. If it doesn't fit, it doesn't fit, right? Depending on the type of machinery I'm creating, it might be much more appropriate to have a hole that was too big and give yourself a little bit of slack lining stuff up. It might be very difficult to deal with a hole that's too big. It's also equally difficult to deal with a hole that's too small. So depending on the setup we have, when would it be better to do a one-tail over a two-tail? I don't know if any of you remember the chocolate chip cookie lawsuit. Chips Ahoy. Any of you have Chips Ahoy chocolate chip cookies? They used to have a slogan, 1,000 chips in every bag. So a bunch of school kids took a bunch of cookies and washed away the cookie dough and kept the chocolate chips and counted them. Guess what? The average was below 1,000. Do you know what Chips Ahoy did? First of all, they gave the school a year's worth of chocolate chip cookies. But second of all, they took the slogan off the back. If it had been more than 1,000, they would have been perfectly fine. A one-tail would have been perfectly fine. But it was too small. Speed increases. Internet speeds. You hear this sort of one-sided argument frequently. Doing a test and tell me whether or not Verizon is telling me the truth about my internet upload and downloads. Okay, I still need to figure out how to calculate the value. How do I find the critical value here that will allow me to decide whether I accept or reject? Well, if that's a z-score, I need to know some things. If I don't know enough things, I might need to use something else. What could I use instead of a z? We'll talk about that on Friday. I will see you all then. Have a wonderful rest of your day.